Okay, so today we're going to be graphing absolute value again, except for this time we're going to be doing something called a dilation. Now, this is where we either stretch it towards infinity or we stretch it towards zero, which is going to be called a compression. And now, this is one of the topics that we're going to get into is we're not really sure whether or not we're stretching the graph or if we're just stretching our perspective. We're going to be unable to tell the difference from this point and in many future lessons. So we're not necessarily going to worry about where this change is coming from. Is it coming from us or is it coming from the math? So let's take a look at our first dilation. Our first dilation is a very simple dilation. We have a negative sign out front. And if we remember, yesterday we said our parent graph always had a perfect diagonal right through the origin. And there's my y equals the absolute value of x. What we're going to do is we're going to see what happens when we have a dilation of a negative number. Well, let's go ahead and let's make a table of values for some numbers that we used yesterday. -2, -1, 0, 1, and 2. So I'm going to plug all of these in to my equation. Now, here's the thing. My equation says I have to take the absolute value and I have to make it negative, which many of us look at and we're like, can we do that? Can I plug in a -2 and get something other than a positive number? Well, let's take a look at the order of the steps. So after my first iteration, when I plug in the absolute value brackets, that negative didn't go anywhere. But my -2 did become a +2. And same thing with each one. My negative didn't do anything, but my -1 is now a +1. My 0 is still a 0. My +1 remains a +1, and my +2 remains a +2, which means that we actually just have negative values. Boom. And so if we graph these points at -2, -2, -1, 0, we see that our graph has completely flipped upside down. And boom, there's our first dilation. We've taken the graph and we're now looking at upside down. Now, did that come from the graph being manipulated? Did we compress it through the origin? Did we change our perspective? Are we now looking at it upside down? That's going to be difficult to prove. So let's just understand that that is a dilation. Some perspective has been changed, and let's move forward. Another common dilation is going to be if we have a 2, which is going to be what we call a stretch. So let's take a look. Let's pop this, our parent graph, onto the grid. Y equals the absolute value of x. Let's see what happens if I have a 2 out front by making an XY chart and using those common values that we've been using. Now we're going to pop each one of those in to our absolute value brackets. I'm going to plug in a -2, -1, 0, 1, and a 2. After my first iteration, anything inside the absolute value brackets becomes positive. And then I double it, which gets me 4, 2, 0, 2, and 4. So what I notice is that my graph, each one of my points has doubled the y value. What was a 2 right here is now a 4 right here. We literally doubled the height of each point. And so it looks like I'm going up 2 over 1 from each one of these. Y equals 2 absolute value of x. And so what was a perfect diagonal of going up 1 over 1 every single time is now a slightly stretched diagonal of going up 2 over 1 each time. So let's see, let's do one more. See if we can't spot a pattern going on here. So I'm going to graph my parent graph that is a perfect diagonal of y equals the absolute value of x. And I'm going to say, okay, what's going to happen with the 1/3? Well, if that made it taller and skinnier, I bet you this is going to make it the opposite. I bet you it's going to make it shorter and fatter. Well, let's try it out. -2, -1, 0, 1, and 2. That's what we have right here. So we have our 1/3 of a -2, -1, 0, 1, and 2. And after my first iteration, everything inside the brackets becomes positive. And after my second iteration, I get a 2/3, 1/3, 0, 1/3, and 2/3. And so I notice that each one of these looks like it's gone down a significant amount. Which in this case, I bet you if I continue that further, 0, 1/3, 2/3, I bet you that would be 3/3. And if I plugged it in, 1/3 of 3 is 1/3 of 3, which is 1. There's my next point. And so what we notice is that there's a pattern going on with this diagonal. I was going up 1 over 1 with the parent graph each time. Now this time, between my origin and my next whole point right here, I went up 1 over 3. So where do I see an up 1 over 3 on my equation? It's the number out front. So I bet you if we use that, we won't need to build a table. We can just find the vertex and follow that slope. So let's give it a shot. Let's see if I can do that to this problem. Well, if my perfect diagonal on my parent function was 1 over 1, and I reflect it across the y-axis, I bet you this one is going to be down 5 over 7. Well, I can't fit that on there, so what I'm going to do is I'm going to say my graph is by 2's, which shouldn't change my parent function, because instead of going up 1 over 1, I'm going up 2 over 2, which is the same thing. So if I do these by 2's, I'm going to put a point in the middle. I'm going to go down 5, 2, 4, 5, and I'm going to go over 7, 2, 4, 6, 7. And I'm going to mirror that. Instead of going over 7 to the right, I'm going to go over to 7 to the left. In fact, this works. We can just simply look at this number right here and see what the rise and the run are. Here we have a rise of -5 and we have a run of 7. If you wanted to test those points, you could. If I wanted to say, can I plug in and get this number? Well, let's see. If I plug in a -7 into my -5/7, -7, that's -5/7 of +7, which cancels out. That is a -5, which is indeed that point right there. If I plugged in a 0, -5/7 of the absolute value of 0, which means -5/7 of 0, which is 0. That point's included. And even if we include a +7, remember, because of the nature of the absolute value brackets, it doesn't matter where we started, it ends up being a positive, which cancels out, and I get a -5, which is in fact that point. So yes, this method does work. And even if we have other translations in the equation, I know that I can read these as okay, that's a left 2 and up 2. So left 2, up 2, that's where I'm going to put my vertex. This negative 2 over 1 tells me I have a rise of negative 2 and a run of 1. So rise negative 2 and run 1, and then reflect that in the other direction. So when I go to the right, when I run to the left. And I notice that this works extremely well. So we get this graph. In fact, any graph, as long as we move it and then stretch it, we're good. So even with this one down here, I'm going to be moving it to the right by 4 and down 1, and I'm going to have a rise of 1 and a run of 5 in both directions. So right 4, down 1, there's my vertex. If I rise 1, run over 5, well, that's way over here. If I rise 1, go over 5 in the other direction, I get that right there. So, kind of missed my point there, but let's assume that went through there. So anytime we have an absolute value function, we know the slope and we know the starting point. And that's all we need to graph any absolute value function. So now that we know how to graph absolute value graphs, we're going to graph something a little more fun. These are called piecewise graphs. In piecewise graphs, for lack of a better phrase, they're like Frankenstein graphs. We take a little piece of this and a little piece of that, and we just smash them together, and we create this new Frankenstein monster, of which we're going to call, from this point forward, piecewise. Because Frankenstein was a wise and peaceful monster, right? Yeah, we all know that. So let's move forward. So even though the graph should go on forever towards infinity, we're going to keep it within the bounds stated. We know the fact that, let's say, like with Frankenstein, that arm came from a whole human being, but we don't care about the rest of the human being. We just care about the arm, and we stick it on our monster. So this is going to tell us what parts of what monster we want. Now, there's going to be a border here. And what I've done in this section is I've listed exactly where the border is. Next section, we're going to be going over how it's actually going to look instead of listed like this. So what you can do is you can say, hey, I have a left of 0 and a right of 0 graph. So I'm going to be doing my left of 0 graph in red, and I'm going to be doing my right of 0 graph in blue, and I'm going to go ahead and draw a border in purple. So my 0 is going to be a vertical line right here where I separate my graphs. It's going to be on left side and on right side. So let's take a look. The left of 0 is x plus 2. I know that this is a right to absolute value equation. So I'm going to say 1, 2. And because the number out here doesn't exist, I know this is going to go up 1 over 1, up 1 over 1, all the way. Even though I know it keeps going forever, I stop at the boundary. So it's just going to be that piece. And it's going to mirror, so it's going to go up 1 over 1, up 1 over 1, up 1 over 1. It's going to continue on forever over in this direction because guess what? There's no boundary. So here's my y equals the absolute value of x plus 2. My right of 0 is x minus 2, which tells me, oh, I straight up described that wrong up here. That is a left by 2 movement, because my minus 2 is going to be my right 2 movement. So I'm going to take my vertex and move it 2 spots to the right. And I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and I'm going to graph going on towards infinity, and I'm going to mirror that off to the left, up 1 over 1. Ooh, but I can't go on past the boundary, so this is my y equals the absolute value of x minus 2. And it's as easy as that. So we're going to take each graph, and I'm going to graph the part of the graph to the left and the part of the graph to the right. And that boundary can be anywhere. As we see with the next one, this boundary is at positive 2. So at positive 2, I'm going to draw myself a nice fat boundary. And I'm going to say, okay, cool. My left of positive 2, I'm going to draw in red. And this hasn't moved, and it hasn't been scaled, so I know it's the parent graph. which is that, almost perfect diagonal, but it stopped at the boundary. And then a perfect diagonal off over in this direction. So I'm not going to draw an arrow here because guess what? This continues. Does my right side continue? No, it doesn't. So here's my y equals the absolute value of x. It goes off to the right and stops, and it goes off to the left and doesn't stop because it goes on forever towards infinity. I'm going to draw my right side in blue. And now this minus 5 means it's been moved 1, 2, 3, 4, 5. There's no coefficient right here, so I know it's actually going to go up 1 over 1 and up 1 over 1 all the way until it hits the boundary. Now, depending on how you scaled it, you might actually have some values off to the right, which is why I drew an up arrow, because it is going up. Does it go beyond this boundary? No, it stops. So I'm not going to draw an arrow this way. There's my graph. So it's not too bad. Most of these are just going to be as simple as left of the number and right of the number and knowing where our transformations are going to put that vertex. So left of 1, 2, 3, negative 3. I'm going to draw my boundary at negative 3. I know my left one, I'm going to draw this in red. And now in this case, not only has it moved, in this case, to the left 1, 2, 3, 4, this has also been moved up by 1. So my vertex is up here. And I draw my line going to the right, and it stops. I draw my line to the left, and it doesn't stop. So it continues on forever in that direction, but it stops right there. My graph to the right. Okay, this has been moved to the right by 1 and up 1. So my graph is right there. And I just go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And then I reflect that movement all the way back here. And so then the question I ask myself is, does it continue going to the right? Yes, it does. So if it continues, I go ahead and I put an arrow. Second question is, I ask, does it continue going to the left? No, it stops right there. So I'm not going to draw an arrow to the left because it doesn't continue. So let's try one more. So again, I have my left of 0 and my right of 0 that I'm doing in red, and then my right side I'm doing in blue. So again, I have my border right along 0. In this case, I have a x plus 1 and an x plus 2, which means that's left 1, up 2. Again, that coefficient is positive, so I'm going to go up, and I hit the boundary. And I'm going to go up when I don't hit a boundary, so guess what? I keep going. There's my y equals absolute value of x plus 1 plus 2. And then over here, I have minus 1, which means it's been shifted to the right one, but in this case, it's moved down by 2. So I'm going to draw my absolute value graph like this. I'm not going to draw an arrow to the left because it stops right there, but I will draw an arrow to the right because it keeps going. And there's my y equals absolute value of x minus 1 minus 2. And then the last two, just to see a little bit of what we could see. This one's at positive 1. And this is the first one that I have, that I notice I have a coefficient, which means this isn't going to open up. This one is going to open down. So I'm going to move left 1, 2. And instead of opening upward, I'm going to have a slope of down 1 over 1, down 1 over 1, down 1 over 1, until I hit that boundary. And does it continue beyond the boundary? No, it doesn't. So I stop, I don't put an arrow. But on this side, does it keep going? Yes. So I draw my arrow. On my right side, you notice how there's no negative coefficient. So on my right side, 1, 2, this one still opens upward like normal. It continues over here. It does not continue to the left, so I don't put an arrow. And so, can I have graphs that are oriented differently? So far, we've only seen graphs that both open upward. Does it matter if they open upward or downward? No. Would it matter if there was a number like 12 in front of it? No. We just graph the graph that's over here, and we graph the other graph that's over there. And we're happy. Okay. Now the last one's a little tricky. So take a moment, pause the video, see if you can't solve this one on your own. Okay. So if you've tried to solve it on your own, you'll notice that these boundaries aren't the same thing. Left of -2, which means I'm going to have a boundary right here, and a right of +2, which means I'm going to have a boundary over here. Okay, let's see what's going on. So my left of -2, I'm going to do in red. That means I've shifted to the left 4 and down 1, so 1, 2, 3, 4, and down 1. I'm going to draw, because there's no coefficient, it must be a slope of 1 over 1. It stops right there. And then I have reflected, and because it doesn't stop, I draw my arrow. Okay, so y equals the absolute value of x plus 4 minus 1. And for my right one, now this is to the right of +2, so it's not right here, it's over here. So 1, 2, 3, 4, down 1. I go up 1 over 1, and because it continues, I draw my arrow, and then I go up 1 over 1 in the other direction, and because it doesn't continue, I don't draw my arrow. And that is my y equals absolute value of x minus 4 minus 1. So what happens right here in the middle? Well, according to this, nothing. So there is no graphs, this is empty. Do you need to write empty? No. But this middle area is empty. We could either put a middle graph if we wanted to, or we might say, hey, these graphs only work if it's below a certain value or above a certain value. And when might we see that? Well, we could see, let's say these graphs represent emotions or feelings. Let's say your bank account is really negative. Well, you could have some feelings about that. Let's say your bank account is really big and you have lots of money in there. You could have some feelings about that. Let's say your bank account is just kind of hovering around 0. You may not care. This may be completely normal, so there's no emotion. So is it normal for graphs to have gaps? Could be. In real life, we see it every day. This is what it'll look like in math. And there we go. So today we're going to be graphing piecewise graphs, and we're going to be graphing true piecewise graphs in true piecewise notation. The only other way that you may see this notation is in interval notation, which is not going to be what we see today, but we will cover interval notation in a later video. So a piecewise graph, it changes between one spot and the next. The boundary is only included in one graph. This is shown through the inequality. Now, what that means is the fact that, again, I'm going to have this graph and it's going to have two different pieces. Today, I'm going to be graphing in pencil because we're going to need to be able to erase some of this. Now, that's strictly because of the method that I show. What I show is that I'm going to look at each one of these and I'm going to graph both these graphs in their fullness, and then I'm going to apply the boundary restrictions. So let's go ahead and let's review a few quick rules on how things work. If I have a y equals mx plus b, that's going to be a line. I know that that's going to be my y-intercept. I know that my m is going to be my slope, which is also my rise over my run. So I'm going to be graphing according to that rule. If I have something that's like y equals the absolute value of x, I know that if I add anything inside the parentheses or inside the brackets, that's going to be moving to the left. If I subtract anything inside, that's going to be to the right. I know if I add anything outside, that's going to be up. If I subtract anything outside, that's going to be down. So I'm going to follow these sets of rules when we're going through this today. So let's take a look. So again, I'm going to be graphing these in pencil. I know that this top one is going to be y equals 1/2 x. That's going to be a line according to my rules. There's no y-intercept, so I have an intercept at 0, 0, and my slope is going to be up 1 and over 2. So if I go up 1 and over 2, I'm going to create a line just like that. I'm going to go down 1 and back 2 as well. Cool. So I have a line just like that. There's my y equals 1/2 x. For my other graph, y equals -x, well, that is also a line. There's no y-intercept, so it also goes to that point, but it goes down 1 over 1. So it is what we call a perfect diagonal going down. Cool. Y equals -x. Awesome. So I have these two graphs, and what I need to do is now I need to plug in these boundary restrictions. So what I'm going to do is I'm going to quickly highlight, I have a boundary right at -2. So I'm going to draw a quick dotted line, which is not technically part of the graph, but it shows me, okay, that separates my graph into a right side of -2 and a left side of -2. So we're going to see, okay, which one's on the left and which one's on the right? Well, let's go ahead and let's make this one in red. My 1/2 x, which is the one that's sloping up, is only for x values less than -2. So it's only going to be for values less than -2, which means it's to the left of my boundary point. It's only the values over here. I don't actually look at anything on the right-hand side. So if I have that 1/2 x, I'm only seeing this little piece. So I'm going to highlight this little piece in red, because that's the only part I truly graph of my graph. I don't actually include the boundary point, so what I do is I'm going to draw an open circle on that boundary point. For my other graph, I'm looking at values greater than or equal to -2. So I'm going to find my boundary point and say, hey, of this whole graph, I'm only graphing this part. I'm not graphing the portion of the graph that's less than -2, only the part that's greater than -2. So what I'm going to do is I'm going to highlight this in blue. And this actually includes the boundary point, so I'm going to fill in a circle. So that is actually my graph. And the reason why I do it in pencil is the fact that I tend to like to go over and kind of erase the part that's not included. Now I'm going to leave a little bit of a shadow just so you can see that the graph actually would go there if it weren't for these domain restrictions. But we know that the only part of the graph that we truly use is this part of the red graph and that part of the blue graph. Nothing else exists. Go ahead and list that in blue. Perfect. Kind of get the idea? Let's try a different one. So on this, I have y equals 7. Now that's going to be in my y equals mx plus b format that we have way up here. The only problem is we're missing the mx, which means that must be a slope of 0 because it disappeared. And if I have a slope of 0, that's going to be a flat line. It's going to be a horizontal line. So because I don't have 7 on my graph, I'm going to make my graph by 2s. So 2, 4, 6, 7. And my graph is going to be a horizontal line, just like that. This is my 7. my absolute value equation, we remember that that gives the shape of a V with a vertex right at the origin. And both the legs of the V are going to be perfect diagonals going to the right and going to the left. And so here I see that I have one that's less than 2 and one that's greater than or equal to 2. So I know right here there's something going on. So I'm just going to make my boundary a little thicker so we can see it. So one of these is going to be on the right-hand side and one of them is going to be on the left. So what I'm going to do is I'm going to graph my 7 in red. Well, that's going to be less than 2. So I'm going to find my graph and say, okay, less than 2. Well, less than 2 is on the left, which means that I don't deal with the right. Less than 2 is over here, which means I only have that portion of my graph. So I'm going to highlight it in red. Cool. And I don't include my point. It's an open circle, just like that. My absolute value equation is greater than or equal to 2, so I know I'm using that part of the graph, which only exists right here. And now you kind of see the reason why I graph the whole graph and then go back and erase the portion of my straight line that I don't use, and I erase the portion of my absolute value that I don't use. Now, you might ask, why do I do this? Well, if I graphed this, does this straight line look like an absolute value? Oftentimes, no. A lot of students expect to find the bend. And so what I do is I graph the full thing so I know exactly where that vertex is. And I'm like, oh no, that's an absolute value equation. We just don't see where the vertex was. Sometimes students will want to put a vertex in there and just randomly put a bend. That doesn't work, so that's why I always graph the full thing and then go back and erase it. So I have a 7 and an absolute value of x. Cool. So let's do a few more. So here it looks like I have a barrier at -1. So I'm going to go ahead and I'm going to slide a value at -1. Ooh. And just realizing I actually drew my barrier a little bit too far to the right because I counted these by 2s. That barrier should actually be at the 1 tick mark because remember the barrier was at 2. So I should scoot that over. Unfortunately, I didn't pen. So what we'll do is we'll just scooch the whole thing over. Cool. Let's take a look at this one. So if I have my barrier at -1, what I'm going to do is I have what looks like an upward line with a positive slope of 2x. It has a 0 y-intercept. So I'm going to draw a line that goes up like this, down 2/1, down 2/1, boom. So it does something like that. That's my 2x. My -3x goes 1, 2, 3/1. So it goes down like that, up 3, back 1, up 3, back 1. That's my -3x. And so I see that the lines are each split on the left and on the right. And so what I'm going to do is I'm going to say, hey, I'm going to graph my 2x, which is less than or equal to -1. So I'm going to find my barrier, find my 2x line, and say, okay, if it's less than, that's to the left. So I'm only going to graph that little piece down there. And I'm going to fill in my circle because that boundary point is included on that one. And my 3x, well, if that was less than, my 3x is greater than, which means it's the other side. Or my -3x, I should say. So I'm going to graph the right-hand side of my -3x. And I'm going to draw an open circle on the barrier because that is not actually included. Boom. And there we go. I go back and I erase the portion of the graph that isn't actually included, but I just left it in there so that I could tell that I graphed the thing correctly. There we go. We have a piecewise function of y equals 2x on one side and -3x on the other side. One or two more. what happens if I have 3 values? Well, that just means that I have 2 barriers. I have a barrier at -3, which I notice that juts up against -3, and so does the next one. So -1, 2, 3. So I'm going to have a barrier right here. I also have another barrier at 4. This one juts up against 4, and as does that one. So it's going to be right there. Cool. So I'm going to do my first one, 4, which is going to be a line right up here at the top. There's my 4. My 0 is right here in the middle. And my -1 is down there at the bottom. Now my 4, I'm only concerned with x is less than -3, which means if I go find my -3, I say, okay, am I looking at greater than or less than? I'm dealing with x is less than. So I'm looking at the less than portion of my graph, so only that little piece up there at the top. So I'm going to draw a nice thick blue line just to make sure that we get it. I'm going to draw an open circle because my point itself is not included. It's actually included in this one. My -3 is included on my 0 line. And I go from -3 all the way until 4. So I actually shade all of this in. Cool. So my 0 line, I included the 4 on the left, my 0 in the middle, which means I bet you that 1 is going to be on the right. And sure enough, yes, x is greater than or equal to 4. So I'm going to go find it, I'm going to fill it in, and shade it in to the right. Oh, and there we go. So it's not too bad. I'm just going to make sure that we go back and we get rid of the pieces that we don't actually need. Cool, and there we go. I have left piece 1, I have middle piece 2, and I have right piece 3, because it says less, between, and greater. Awesome. Let's do a few more. If I have y is equal to x, I know that that's going to be a perfect diagonal right through there. Y equals 2. Well, you know what? What I see is that my barrier is at 5, so I'm going to go ahead and make these by 2's. Which means that my 2 is going to be 1, 2, 1 block up. So there's my 2. And then my 2x, that's going to be up 2 over 1, up 2 over 1, down 2, back 1, down 2, back 1. I have that. So I have my 2x, my x, and my 2. Perfect. So now I'm going to go ahead and draw my boundaries. I have 1 at -5. So remember, we're doing these by 2's. So 2, 4, and 5. So I have a barrier right there. Also, I have another barrier at 0. So I'm going to go ahead and I'm going to draw my barrier right down the middle. All I'm going to do is I'm going to say, hey, my x, I'm only dealing with values less than -5, so I'm going to find my x, find the -5, and say, hey, less than is over here, which means I'm going to cover up the stuff on the right. So I'm only doing this. And I'm including that point on the barrier. The next thing, my 2 is in between -5 and 0. So I'm going to find my 2 boundaries and say, hey, I'm only dealing with this little piece in between these boundaries. So I'm going to draw a nice thick line. I'm going to include neither end. Boom. I got that. My 2x, what I'm going to do is I'm going to include that to the right of 0. Anything that's greater than or equal to 0. So I find my 2x. I find my 0 point, which is going to be right here. I go ahead and I shade it. I'm going to fill it in because that is actually an included point. So I have that And I go back and I erase the unused portions of my graph. Get rid of that part of my x, get rid of that part of my 2x, and these parts of my 2. Boom. And there we go. I have a piecewise function of y equals x, comma 2, comma 2x, given these domain restrictions. Last one. Y equals 4 is going to be a horizontal line. X plus 1, that's going to be a v that has shifted up by 1. Boom. Got that? And then negative 1, that's another horizontal line. Awesome. So I'm going to find my boundaries at negative 3. So 1, 2, 3. I have a boundary right here. And then again at 1, I have a boundary right here. What I'm going to do is I'm going to go through and I'm going to graph them one by one. My 4 is where my x is less than negative 3. So I find my negative 3 and say, hey, the less than piece is the one piece way up here. It's not included. So it has an open circle. My V shape is going to be between negative 3 and 1. So I actually get this whole portion of the V. And what we notice is the fact that even though that point wasn't included in my top graph, it is actually included in my second graph. And we'll talk about what that means in just a moment. My negative 1 is going to be down here. Boom. And there we go. We go back and we erase the portion of the graph that we didn't use. So I get rid of the right, I get rid of the right, get rid of the left over here, get rid of the left over here. Boom. And that's it. So the only thing that we have left that we're not really covering today, but it's a good point to notice, is this makes the graph continuous. We notice that even though it was not included with one of the graphs, the next graph actually did include that point. So if you were to try and trace the graph with your finger and say, this works, this works, this works, this works, this works, this works, you would never need to pick up your pen or pencil with tracing positive points. Now all of a sudden you would change direction, but what would happen is this allows the graph to stay continuous. Unlike right here, where the graph jumps from one to the next. That is not continuous, that is a break in the graph. There we go, that's all for today.